I'm Michael Montgomery from Kinetica. My co-presenter is Kevin MacLean from RJC. What we're going to be discussing here today is the viscoelastic coupling damper, which is an extremely efficient system, damping system for high-rise buildings. Kevin MacLean is going to be discussing the implementation of this technology in an extremely tall, slender building in downtown Toronto, shown right here. So this is the viscoelastic coupling damper. What it essentially is layers of high damping viscoelastic material that's bonded in between steel plates. These replace elements in the structure that undergo significant shear deformation, such as outriggers, coupling beams. This VE material transforms vibrational energy into heat. So this is kind of an overall of the system here. So it's a pretty simple construction technique. The elements in yellow here are these viscoelastic modules. We configure them in these common structural configurations, coupling beams, outriggers, and in turn this adds distributed viscous damping for the building. Now these viscoelastic modules here, these guys in yellow, are completely replaceable. So as a lot of you guys probably know, viscoelastic dampers was actually the first damping system used for tall buildings. That was in 1969, and since then, there's been over 250 buildings that actually have used this type of material. Now, it's evolved quite a bit from then. The material has evolved, and it's quite an advanced material right now. And commonly, it's being used in brace and wall configurations to kind of to be used in these racking type configurations in buildings. So the viscoelastic coupling damper is just a new configuration of viscoelastic dampers. So here we have these common wall configurations and brace configurations. All we're doing is we're applying this to tall buildings that in an extremely effective way to kind of get this large shear deformations and add viscous damping to the building structure. And what we have here is we can connect to the reinforced concrete structure in many different number of simple anchorages. So just to briefly talk about the kinematics of the coupling damper. So, dynamic earthquake wind loads cause large rotations in these big concrete walls, and that in turn causes shear deformations in the VE material itself. So you can see here that this material is undergoing a lot of shear deformation. So this adds this distributed damping to the building structure. So I just want to talk briefly about the viscoelastic material itself. So here, this is the hysteretic response of the material to a dynamic load. This is the equation that represents the actual response here. So when you have a dynamic loading, you have both an elastic and viscous restoring force. And what's really interesting about this material is is that you can highly engineer the actual damper itself, because the force, stiffness, and damping coefficients are completely related to the area of the VE material that you have in the damper. So unlike many damping systems out there in the world, viscoelastic damping provides damping over all amplitudes of vibrations. So this is very important when you're talking about multi-hazard and also, different types of loading on your structural system. So here you can see here, this is all dynamic loading. This is on just a small scale specimen here, but we have all the way from 12 millimeters to 50 micrometers. And actually the manufacturer has even gone to smaller displacements. But as you can see here, it's a very well-behaved hysteretic response over all the amplitudes of vibration. So that's good for 1 in 1 month wind loads through 1 in 2,500 year maximum credible type earthquakes for your building. So with this, there's kind of a wind and earthquake integrated design philosophy. So here, kind of these elements here are actually structural fuses. We use them adjacent to these viscoelastic modules. And we capacity design these structural fuses such that at a given force level, they actually activate. And that in turn protects the walls and protects the integrity of the structure subject to large earthquakes. So you can see here, this is kind of, we call it the cat's eye hysteretic design envelope because it literally looks like a cat's eye. So we have here, this white element here is the viscoelastic response. This is for low earthquakes, wind loads. And this element here in black is this viscoelastic-plastic response. So this is the response that you're intending to get for a very large earthquake. So I'm just going to go through a few tests that we've done on this system. So here we have some wind dampers that we test, as well as some seismic dampers. As you can see here, these seismic dampers have structural fuses built in on the side. These are called reduced beam sections. They're essentially the weak link in the overall damper. Now, we have here quite a big test setup. We had to test these things in full scale because they're going into tall buildings. So what we have here is 6 reinforced concrete post-tension buildings. The reason why we used post-tensioning and RC panels is to actually get this realistic behavior. And here we have the actual damper that's being tested. Now we have 4 pins in the system, which allows it to kind of create this racking movement back and forth. And we actually have actuators that kind of launch off the wall here that actually push the system and actually create this shearing force or shearing deformation in the VE material. So here again is the overall test setup. This is me much younger. So you can see it's a fairly large test. And here is the deformation of the viscoelastic material in this test. So you can see here it's primarily a shear response. And this test is engaging it like it would in the actual tall building application. So here's one of the tests we're doing. Here we have the hysteretic response. You want to watch that. And then here you can, if you look at it, you want to see the deformation of the actual steel plates here. So here you can see this viscoelastic response. It's elliptical in nature. So this would be kind of typical to what you would get in, maybe, say, a wind vibration or a low-level earthquake. Now we're scaling up the amplitude of the deformation here. So now we're going to a maximum credible type earthquake. As you can see here, the response is much more violent in nature. You're getting responses from other modes, not just the first mode of vibration. And in this case, we have structural fuses, which are right here and here. And so you can see here that the force is capped off. Now we're going to go one further. Now we're going to push the system and actually fully plasticify these structural fuses here. So you see here, this is transferring from that viscoelastic response to now a viscoelastic-plastic response. This is protecting the walls, and all of the good energy dissipation is now happening in these steel sections here. So this is very important for the earthquake design, performance-based design of your building structure. Now, just to kind of sum up kind of the resiliency of the system to service level earthquakes, where Kevin is actually going to be discussing a structure that's a wind sensitive structure in Toronto, but I just want to go over these briefly. So I mean, this is a coupling beam after the conception earthquake. This is what as structural engineers we're currently doing and designing. We're designing our buildings to have kind of this non-linear kind of response in coupling beams effectively. So the issue with this is, how are you going to repair that? What is the performance after it? And what do you do with the building afterwards? So that's one aspect that we think the viscoelastic coupling damper really comes into play. So for service level earthquake, again, it's added damping that improves the performance, accelerations, forces, drifts. Maximum credible earthquakes, we have a similar response, but less damage expected in the viscoelastic damp system. And we have modular units that are much more easily replaced than a traditional concrete reinforced beam. So lastly, some of the benefits we see constructing with VCDs is primarily in a wind-controlled structure. VCDs replace heavily reinforced concrete beams. i.e. they do not take up any space that the building owner might want to use. For example, penthouses, in high real estate value places like New York City or Shanghai, etc. The speed of construction, these are modular units, so they can actually be installed off the critical path. Performance, again, these viscoelastic dampers are effective for all earthquakes and wind loadings. Reliability, the VE dampers were used and were the first damping system ever used. Since then, the materials evolved substantially. It's now a fourth generation material, and it's manufactured by industry leaders, Nippon Steel and Sumikin Engineering and 3M. Maintenance, there is no maintenance, monitoring, or tuning required with these systems, so that's quite different from other damping systems out there in the market today. So with that, I'm going to provide it to Kevin. He's going to talk to you about the implementation of this technology in a tall building in Toronto.
Thanks, Mike. So I've been fortunate enough to be involved with this project for a number of years, and RJC has a long history of working with Kinetica on these devices. My colleague, Dr. Tibor Kokai, was one of the original contributors to the device. And I think it's important to discuss the history of this particular project because its evolution actually was sort of key into demonstrating how this is a very efficient technology that could be implemented in a tall, slender structure. So just a basic sort of overview of the project itself. It's a project in downtown Toronto. It's 63 levels to the roof. It's about 200 meters tall, and in its current configuration is very slender. It's about 10.5 to 1. Obviously, we need supplemental damping. We looked at a number of different lateral systems or variations of a common system, a number of different damping systems, and I'm just going to talk a little bit about how the project evolved over the last almost 4 years. So early on, we were engaged about 4 years ago. There's a little mistake on the slide, by the way. That's supposed to be a coupled shear wall. When we started with the project, we came on board, and essentially this early scheme was already schemed out. It's not sort of very attractive from a structural perspective. It's kind of just a mishmash of coupled shear walls all over the place. At that time it was 56 levels, and it basically matched an architectural layout that was sort of prepared at the owner and architect's behest. It wasn't particularly slender, 8 to 1, but when we started this job, we knew that the owner wanted to go taller. We did a quick ETABS on this, and it kind of confirmed our suspicion that we were going to have a torsion problem. So then essentially at that point, knowing that this thing's going to get taller and we already have a torsion problem, we basically sort of redesigned the structure and worked with the architect to rework the suites into what we affectionately refer to as our Strongwall scheme. We basically took all these shear walls, smashed them out into these two big strong lines that are very stiff in torsion, and these coupling elements are working quite hard in this scheme. So the height increased. We're sort of at 9.5 to 1. The torsion problem was quite diminished, but obviously we had some acceleration problems. And then the final pass, after some negotiation with the city, there were some setback issues which basically forced the tower to squeeze. And just to give you some idea of the site, there's a major street on one side, a heritage building abutting it on another, an alleyway and a road. So they increased the setback on the main sort of street and they relaxed it in the north-south direction. But essentially the volume of this building was totally fixed, and the 200-meter height is basically due to a shadow restriction on a neighboring park. So we basically had this sort of rectangular volume that we couldn't do much else with. And the walls that we were sort of allowed to put in terms of thickness for a 60-story building, 650 mil thick walls when there's only 2 of them was pretty lean. So I'm just going to run through sort of the evolution of the numbers. I'll try not to spend too much time on this, but essentially our first pass, as I mentioned, at desktop level, at 56 floors, the accelerations were reasonable. The building was a little on the soft side, first mode period at 5.9 seconds. You can see that translation north-south and torsion was pretty heavily coupled. So this, no problem. That was pretty much a problem at desktop. The torsion was quite high. So obviously, as I mentioned, we went to this scheme with these 2 stronger walls. At this point, we still had some drift problems. I'll obviously get to this in a second. So we basically put some not so great outriggers grabbing onto these columns, and at mid-level mechanicals we did have a belt at one point. These suites are interconnected on some levels, so we couldn't put a wall there. So at that height, obviously you can see that the torsion came down to a more manageable level, but 26 milli-G at 10-year is not going to cut it. You know, as we sort of knew all along, we would be going with a supplemental damping system for the project. Then came making the project narrower and longer, which should have made it markedly worse, which was somewhat the case, but we were fortunate enough to have a neighboring project come up here which gave us a bit of shielding. This tower is quite close in proximity to our tower, and they're actually on about the 3rd level, so RWDI tested this with and without our neighboring property. So if you see an asterisk in terms of shielded, that's the condition that we were talking about. The neighboring project is kind of in this area. So growing it to the north actually didn't pose so much of a problem because it was pretty well shielded by the adjacent property. One thing that did happen that was interesting was these balconies were quite jagged before, and now they've become flatter, shallower, and the pattern of the balconies, this pattern basically inverts, so they kind of move in and out in these blocks. And that actually served to reduce a lot of the drag interaction and the roughness of the tower, and it interrupted some of the vortices just because of the pattern of all this. So that's why basically without doing too much, the accelerations came back down. The torsion dropped a touch just because these walls are a bit farther apart, but you can see at this point we're sort of in the 19-meter wide range to 200 meters tall. So at this point we looked at TSDs, a tuned sloshing damper tank, and the viscoelastic coupling dampers. And we basically went through a very detailed sort of costing exercise with the owner. To give you some idea of the size of the tank, this is sort of the space that it would occupy in plan. It was a bi-level tank, so basically we were looking at something like 10 meters by 10 meters by almost 3 floors tall. And then we looked at these viscoelastic coupling dampers where, as we've optimized the system, they kind of ended up in the middle sort of third of the building, which makes sense. So we went through the costing exercise. Again, these offer good torsion performance and acceleration performance in this sort of narrow direction. And essentially how it all shook out was, in working with the architect, this volume that would have been occupied by the tank was reclaimed, and this is actually a little on the light side. It was something more like 3,500 square feet that they recouped. The architect worked out some nice multi-level penthouse suites. So that's big money for the owner that they can recover by not having this tank there. And again, in some cases you may make the building a little bit taller to accommodate the tank. We were very much locked in this volume. So after working on the project in multiple sort of conditions for a number of years, we kind of ended up at a point where this system has been selected. We're basically in for building permit, we're out for tender, and we're going for construction in about a month and a half. The owner's just finalizing their agreement with the provider of the dampers, which is Nippon Steel and 3M Sumitomo. So basically, through this process, obviously we did a number of optimization studies with Kinetica. We basically left concrete coupling beams everywhere on this core and only used the VCDs on these 2 strong wall lines. That's where, obviously a lot of the deformations occur. And then one of the keys to sort of the successful implementation of the VCD was we elected to, above these kind of outriggers in the podium level, we went with structural steel coupling beams above and below the VCDs, and we tuned their stiffness to drive deformation into the dampers. So it made the damping configuration that we came up with very efficient. The other benefit of this was, because it was a first-time implementation anywhere in the world, really, they served a secondary purpose, which I'll talk about a little bit later, and that is in bounding this analysis. These steel coupling beams were robust enough to take additional shear should the stiffness of the VCD material not be there. So we'll get into that a little bit later. Essentially, the design that we have are these 2 steel rolled sections that are going to protrude from the formwork. We're going with a cast-in section design with the zones sort of passing on either side. And then we have 2 VCD panels which bolt to each side of the web with pre-tensioned bolts. So you can sort of see a section of what we're talking about, an elevation with the forks, and a cut in plan and an elevation. So that's the VCD panel, and these are these cast-in steel forks. We went through quite a lot of discussion with some steel fabricators and formwork contractors to sort out the details of the system itself. So what we came up with was that this this steel section would come with 2 channels bolted to it for installation so that we didn't have to worry about the damper being damaged during erection or anything like that. Each one of these will sort of bolt off later, and the VCDs will come by once the construction operations are out of the way and bolt back in. So you can kind of see these middle 20 floors are where the VCD elements are. This is with the steel channel sort of templates, we've been calling them. And then you remove the template and you bolt the VCD back in, pre-tension these bolts, and do all your quality control with the pre-tension connections. So there you go, you can see them being bolted in. We did a lot of work with RWDI on this project. We were also peer reviewed. We recommended MKA to the owner, and they've peer reviewed this along with us because it is a first time application. So through a number of interactions with RWDI, we recommended and they recommended targeting about 1.1% supplemental damping in the first mode and about 0.6 in torsion. But one of the sort of key aspects to this was we really couldn't degrade the periods too much. We needed to maintain similar mode shapes and similar frequencies. So this table is simply meant to illustrate that obviously in our baseline building, if all else was the same and it was a conventionally reinforced coupled shear wall building, you can see that we've got a very good spacing of the frequencies. There's very little modal coupling, if any. It's very much an X behavior, a Y behavior, and a torsion. So we took all the concrete coupling beams out on these 2 strong wall lines, and we placed the structural steel sections that we'd been optimizing. And you can see that the period doesn't degrade too much. And then at this point, we started introducing the VCDs. And sort of the key to this whole thing was a bounding exercise on our part. We wanted to establish a temperature range that Kinetica could work with in terms of specifying the product. So basically our upper bound is a stiffer stiffness and more damping at 20 degrees Celsius, and the lower bound is a softer temperature. So you can see that we've achieved 1.3% in the first mode, 1.3 in torsion, and then at 30 degrees slightly less, but this well sort of bounds the targets that we've had. And just of interest, what we did was actually remove the stiffness entirely from those middle 20 links, and you can see that the frequency, again, didn't degrade that much. So that was kind of the key to the design. In addition to this sort of bounding that we did for SLS, we basically bounded the ULS design because we essentially this building was governed by building motions primarily and drift to a sort of secondary degree. And with it being a first-time application, we discussed with the owner and the design team a rationale such that these devices would only be required for a serviceability building motion performance criteria. So at the ULS level, basically, we've ignored the supplemental damping for both the modal response spectrum earthquake behavior and in terms of the equivalent static loads that we got from RWDI. So we're not counting on any damping. And we also ignored the stiffness. So we have several different ETABS models where we have no coupling dampers, and we've redistributed the shear up and down to the adjacent steel sections. And we've also put them in at quite a significant increase in stiffness to what their operating temperature would be. So we're looking at them at 10 degrees Celsius where they're quite stiff. And just as an aside, most of our work was done in nonlinear, ETABS nonlinear, but we've done a linear elastic analysis because the K and C values that we're using in these ranges are effectively linear for our purposes. And by bounding it, we've then sort of come up with a temperature range and stiffness ranges, which we've sent to Kinetica. And then as the damper designer, they've done full nonlinear time history in Perform, OpenSeas, and everything else to categorize the damper self-heating and other behavior. So this is just kind of a bit of a summary. We've achieved about a 1.1-ish% supplemental damping. Obviously, as I mentioned, this is a successful project. And this is sort of where we stand right now. This 20 millig's dropped down quite substantially to 15, 16. And you can see our biggest problem was the ISO 1 year. 12 is substantially larger than obviously 9.4. So we're down right in a very optimal range where even at our lower bound, we're still meeting this criteria. And we've bounded it very well. So as I mentioned, basically we've done this bounding exercise in terms of specifying the devices. So we worked through with Kinetica specifying the number of layers of VE material, its thickness, the number of forks, the number of levels, where the levels were. We've optimized the steel links to drive the deformations into the coupling dampers. And then we basically turned all these targets over to Kinetica, and then this is a couple shots from their nonlinear time history analysis. RWDI provided time histories all the way through, and you can see at these sort of spikes, there's about a 30% reduction in the accelerations that you'd see on this time history, and you can see a substantial reduction in the drift as well. Essentially at a time, I'll just power through this quickly. We found that this is an easy construction technique in terms of using a cast-in-place coupling beam embed. The speed of construction could be somewhat increased because these coupling beams would have been very heavily reinforced. Essentially, we've used this device for wind serviceability only, but it offers enhanced performance for earthquake as well. And we've done a quite thorough job in bounding all these criteria. So we've added damping, and we've saved the owner, or given the owner back 3,500 square feet roughly of sellable. So that's basically it. With some acknowledgements, obviously, my colleague Dr. Tibor Kokai, one of the original developers of the device, my colleague Daniel Snodgrass, Konstantin Christopoulos, one of the co-developers of the device at the University of Toronto. There's Jack Gao at Kinetica, who's Mike's colleague and has done a lot of the nonlinear work on this. RWDI, Peter Irwin, and Bouillard, they've sent us an insane amount of data on this. They've been very good to us. We've been in the tunnel multiple times. They've sent time histories, target frequencies. And I'd like to thank our peer reviewer, MKA, Ron Klemencic, Farshad, and Robert Baxter. They've been very good to work with. It's been a very fruitful and productive process with them. And then obviously the damper manufacturers, Nippon Steel, Sumpkin Engineering, and 3M, and Ian Aiken, one of Konstantin and Mike's colleagues. So I think that is basically it for us.